Hello, we are going to go over today about our lecture is going to be about paramagnetism, diamagnetism, and we will explain it with mean field theory. So according to the mean field theory, we need to treat material as collection of some magnetic electrons, and we will apply to them statistical laws. And according to that, we can derive paramagnetism, diamagnetism, and ferromagnetism. So we know that when we consider electrons, we can divide them as localized and delocalized. Localized electrons are those of magnetic insulators, and also some F electrons, transition metals. And delocalized materials are those that exhibit metal-like properties. So let us look at the emerging of diamagnetism in magnetic materials. We know from the electrodynamics, for example, when we have electron in magnetic field, its trajectory will have this spiral-like trajectory. And if we look at the properties of these electrons in magnetic field, we can divide them in absolute frame and also in the rotating frame. So here we have absolute frame consists of X, Y, Z here, and in this frame, our second law applied to this case will look like this formula here. So this is standard Drude-Lorentz model, and according to it, we have magnetic field acting on it, and it creates Lorentz force and also this electric force here. So if we look here the how to this equation and write down in the rotating frame, so we can use here this Euler formula here. So Euler formula here written like this, and it just shows here the transition of the derivative in absolute frame to the rotating frame. So here we have ddt in absolute frame and this dt in rotating frame plus omega multiplied vectorially to that vector VA. So in the case when we have absolute velocity, it is connected to the relative velocity with this formula. Here we have omega times r. This is so-called transition velocity. So if we write down this formula here, we will have this formula for dVr, and we substitute to the formula for the second law, which appears to be written like this. So in this case of rotating frame, we will not have Lorentz force, and according to that, the second term needs to be equal to 0, and from this we conclude that this B minus 2m divided by E multiplied by omega should equal to 0, and we will find here this omega equal to E divided by 2m multiplied by B. So this gives us normal frequency, or also it's called cyclotronic frequency. Now if we find out here this magnetic moment due to this rotating electron, it will look like this formula here. So it is E here stands for the current, and S here is the area of this circular motion, and we will have this equation according to this theory. Now this formula for the magnetic moment appears to be looking like this when we substitute here expression for the frequency, and from this we can see that mu magnetic moment and B magnetic field are vectors, and they opposite to each other. So this is shows us that we will have here this emerging of diamagnetism, because here magnetic moment is opposite to the magnetic field B. Now, if we will look at this classically, so in classical result, in B magnetic field, when we have equal to 0, all these electrons will have chaotic these directions here, and according to this, if we apply magnetic field, according to that theory, each magnetic field, each electron will require magnetic moment equal to this. And since these motions are chaotically distributed, we will have that finally this mu magnetic moment or average magnetic field magnetic moment will equal to 0. So according to this, we will have no diamagnetism, but we have magnetism in these materials. So this classical result shows that we will not have diamagnetism. Now, in the case when we consider all these quantum, if you will apply quantum mechanics to this, so in quantum mechanics we will have this formula for the Hamiltonian, which is equal to P minus ER squared divided by 2m, where I is a vector potential, and the B magnetic field is found by this formula here. And if we use here B magnetic field direct on Z direction, like this in this formula, we will have expression for the vector potential looking like this. So if you substitute this expression for the vector potential in the formula for the Hamiltonian appears to be looking like this in this line here. Now the last term here looks like a potential function of the harmonic oscillator, and we can apply here results of the quantum mechanics for the harmonic oscillator. So in the harmonic oscillator equation, the solution for this using these Lambda operators. So this is creation operator, which will look like in this formula here. And finally, using this creation and annihilation operators, our operator will, Hamiltonian will look like this, just like in the harmonic oscillator problem in quantum mechanics. So here we have HW equals to EB divided by L. Now in this formula, using this theory, we can find out that electric energy levels will be just given by this formula for the harmonic oscillator. And if we use here this last term P squared divided by 2m, it gives us this H squared Kz squared divided by 2m energy levels of the free electron. And finally, this electron will have, these energy levels will have this value. So here N stands for the Landau levels, and these Landau levels can be shown using this picture here. So for here we have magnetic field direction, and according to the theory of Landau, we will have electrons rotating about this rotation, about this direction of the magnetic field, and these different radiuses of the circular motion will correspond to the Landau levels of these levels here. So this is called Landau levels. Now, if we use here statistical mechanics, according to which we have in this large potential or ground potential equal to this here. So we have here EF standing for Himmel's potential, and in this case, this mu is Himmel's potential, and subsequently we will use it for magnetic moment. Now, according to the statistical mechanics, we need to use here this derivative with respect to B and find out this magnetic moment. But this gives us more writing here, and instead of it, we can write down this line here, which according to this energy is equal to just average of the Hamiltonian, and average of Hamiltonian is just last third term in the Hamiltonian, which equal to this. So we use here this equation for the x squared plus y squared is equal to 2/3 of rho squared, and according to this, our mu chemical potential will be just found by the derivative of E with this to be taken with minus sign, and we will get this result here. So according to this result here, magnetic moment is has opposite value with respect to B, and this just gives us non-zero value of the average magnetic moment, and this average magnetic moment will be just opposite to B magnetic field. And according to this, gives us diamagnetic effect, and these materials will have show diamagnetism. So according to the results that we found here, this corresponds to the diamagnetic magnetic constant kappa-L, which is equal to minus 2/3 mu b squared NEF. NEF stands here for the density of states at Fermi level. So according to this diamagnetic constant is given with minus sign, and shows that this corresponds to diamagnetism. Now, if we look for the paramagnetism, so we have here Langevin theory. In the Langevin theory, we consider again collection of electrons here, and this collection of electrons will have chaotic distribution of magnetic moments. And according to the classical electrodynamics, these magnetic moments will interact with external magnetic field. And in this case, this external magnetic field gives us rise to the energy, which is given with this expression here, minus mu and B scalar multiplication. And here theta angle is the angle between the direction of magnetic field and the direction of magnetic moment here. Since they will have different theta angles, we can find here mu, average mu, using this equation here, where P is the Boltzmann distribution function, which has factor here E in EZ divided by T in exponent. Now, using this formula for the magnetic moment, we can find here this magnetic moment equal to this, whereas this L function is so-called Langevin function. It is equal to this expression here. So, according to this formula, again, we can see that that mu is parallel to the magnetic field, and this corresponds to the paramagnetism, because mu and B vectors are parallel to each other. Now, if we look at this problem using the spins, so we know that in quantum mechanics, spin is quantized value, which is given by this equation here, where J is the total moment, which is equal to the orbital moment plus spin moment. So according to this, we can use again this formula for mu and find out this Zeeman for energy, which is equal to this. Now, statistical sum looks like this here, and since this is looks like a geometrical series, we can find here this finally value for Z, which is equal to this expression here. Now, using the statistical mechanics, energy is equal to this 1 over Z dZ d vector, which is d logarithm Z d vector, and finally B mu is just this EZ divided by B magnetic field. So now we will have this expression for magnetic moment, and this magnetic moment is given with this Brillouin function, which is Brillouin function here stands for this function here, and it is given with this large formula here. So according to this, we can write down this picture. This for different values of J, and this different values of J for Brillouin function, they approach this Langevin function for large J values. So this explains our Langevin and Brillouin and Langevin functions here.